So today I'm going to be talking about promoting global stability in data-driven models of quadratic nonlinear dynamics. I know that's a mouthful, but I'll explain a bit about what I'm talking about as I go on here. And the sort of main takeaway here is that data-driven models are often unstable or divergent in finite time, and we're working on new methods that guarantee the long-term boundedness of these types of methods, which we're really excited about because divergent trajectories are no good if you're doing control or you're trying to find a model for how your physical dynamics are evolving. So this is based on a recent paper we have on arXiv and has been implemented in our SINDy open source repo. So please check it out there. So just a rehash, I've described this system identification with this sparse identification of nonlinear dynamics method. I've described this in some previous videos of mine, and I encourage you to look at Steve Brunton's YouTube channel for a deep dive on how these methods work. But basically, what we're trying to do here is we have some measurements of some complicated system, and we want to figure out how are those measurements evolving in time. And we can sort of try and build up a system of ordinary differential equations or partial differential equations for how those measurements are evolving in time. And then use that to forecast, okay, what's going to happen next in this experiment. So what you imagine doing is you have some, I'm going to breeze through this, but you have some system. You take some measurements of this system, which gives you some data. You imagine now you have some data in this x dot, and now you want to figure out what this unknown right-hand side is that determines the evolution of these measurements in time. And this is just going to be some candidate library of possible terms that could be on the right-hand side. And this is going to be the coefficients telling you how strong each of the terms are in this theta. So what this might look like for Lorenz is you have your data of x dot, y dot, z dot here. You have possible terms in this theta matrix all the way up to quintic polynomial terms in x, y, and z. So we're guessing that these polynomial terms might be good fits to the data. And then this coefficient matrix is just picking out how strong each of these terms are in this data matrix. So that's what we're going to do. And the way you solve this efficiently is you solve an optimization problem asking for the set of coefficients which minimizes the difference between the data and the model you're trying to build for it. But at the same time, you're trying to minimize the number of coefficients that you're using. So this is going to try and zero out as many of those coefficients as possible, and that will give you a parsimonious model and avoid some of the overfitting issues that are common in machine learning methods. So that's what you do. And again, if this was too fast, please take a look. There are a lot of good resources on this method. I want to mention further that we can constrain this optimization with conservation laws. This is really nice for fluids and plasmas, which tend to have these conservation laws. So building that in actually gives you the nice physics-informed models that aren't just sort of taking the data at face value and doing whatever it can with it. It's actually constrained a bit by the physics. And then one big question you might ask is, can we actually guarantee that the resulting models are numerically or physically stable? And in general, these methods don't have these guarantees, but we're going to show for a specific class of fluid and plasma models, we're going to build a new method called trapping SINDy, which guarantees or at least strongly promotes these SINDy models to be physically stable and to not diverge in finite time. So they're actually going to have these trapping regions where the trajectories are guaranteed to fall into these regions and stay there for the rest of time. So that's going to give us long-term stability of these models. So let's get into it. So this is based on analytic results regarding the long-term boundedness for fluids with what are called energy-preserving nonlinearities. So this is primarily based on this theorem from Schlegel and Nowak in 2015. Many of you have seen this sort of thing before, but what we're going to imagine here is we have some set of measurements, for instance, of the flow field of an incompressible fluid. So we have some measurements in space and time of the velocity of this fluid, right? And we can decompose that into a Galerkin basis. Basically, we take this pure spatial part, and then we decompose the spatio-temporal dependence into some set of temporal modes and to some set of spatial modes. And in our case, we decompose into using the proper orthogonal decomposition, which is called Galerkin, a Galerkin expansion, and this is sort of a common technique in the field. So that's what we're going to start doing. We imagine we have some measurements of the fluid velocity, and we decompose it into some low-dimensional basis that splits up the temporal and spatial dependence. Now what you can do is you can plug this expansion back into the incompressible Navier-Stokes equations, or you can also do this for ideal MHD if you're working on plasmas. And what you end up getting then is when you sort of work out all the algebra there, so there's some steps, you can reduce it to a system of ordinary differential equations for the spatial modes AI. And the nice thing here is all the, for the temporal modes AI. And the nice thing here is that all the spatial dependence in the system has vanished. It's all contained in these coefficients. And so we just have a system of ODEs instead of a system of PDEs describing how these flow fields are going to evolve. So this is called Galerkin projection, and it's very common. And then there's an additional assumption that is often true in fluids and plasmas, which is this energy-preserving nonlinearity. So in other words, this Qijk tensor satisfies this inequality. You can show it preserves the overall energy of the fluid. And it turns out, yeah, the fluids and plasmas satisfy this in a number of different conditions. So this is actually valuable for many flows that we look at. So that's the setup. Now what we do is we define this matrix AS, and we take the symmetrized matrix L, same L as right here. We just have symmetrized it. We take the tensor Q from which is the same as this Qijk, and then we define some arbitrary M and sort of dot it with the first index of Qijk. Okay, so M is arbitrary right now, but we imagine we choose some M. We can compute this AS because we have these coefficients, and then the theorem follows. So the theorem says there exists a monotonically trapping region at least as small as this ball defined through M and with radius R. So this ball centered at M with radius Rm if and only if the real symmetric matrix AS is negative definite with eigenvalues sort of ordered in this way. And then the radius is Rm of this ball is given by this expression, where it depends on the eigenvalues of AS, so this lambda 1, and this dm, which I haven't defined here, but basically it's a function of this vector m and the coefficients L, Q, and so on that appear in this equation. So we can, if we know what m is, we can compute this, the radius, and we can compute this ball and figure out that exactly what does this monotonically trapping region look like. So that's great, so the takeaway from this is the name of the game is we are going to have to search for an M such that this is true, right? So we can imagine solving an optimization problem where we're changing and looking for this vector M such that this matrix AS is negative definite, and if that's the case, we have the existence of a monotonically trapping region. And that's really great because that means we have global stability, we have long-term boundedness of the model. So how do we actually build this into a data-driven modeling scheme? So, just to recap, so what SINDy models do is they take some measurements of x dot, they build some possible right-hand side term, and then they find the set of coefficients that minimizes the error in that in the ODE, and at the same time it's promoting some sparsity, trying to zero out as many of those terms in the coefficients as possible. So that's traditional SINDy. Now, there are constrained versions of SINDy, so we actually can build in constraints on the coefficients. This is what this last term is doing here. So we're building in some affine constraint where we want c times c to be equal to this vector d. So this is going to sort of be satisfied automatically. And this is how we're going to build in this constraint I mentioned, that the quadratic piece of the model is energy preserving. So that's nice. We can build in this energy preserving piece, but how do we actually push our model building procedure to give us a long-term bounded system via this theorem I just mentioned? And what we do there is we still have this constrained piece, and we add one more term here. And this lambda 1 here is the maximum eigenvalue of this matrix AS. And so what this, and so that's AS is a function of m, right, through this equation. And now we're going to also argmin over m. So we're varying this vector m such that the maximum eigenvalue of this AS matrix is minimized. So we're basically pushing AS into the space of negative definite matrices. And that's how we're going to sort of find an M such that AS is negative definite, and therefore sort of use this theorem to show that there exists a monotonically trapping region, and our data-driven model will be manifestly long-term bounded. To actually solve this, we solve a variant of this, but this is sort of what we're going to do for now. So this is great. We have an algorithm for finding these types of models. So basically what this looks like, I just want to show you, so the blue here is noisy Lorenz data from, again, the Lorenz attractor I showed earlier. And then the white is the model fit as the algorithm progresses in its iteration. So the algorithm has had 0 iterations right now. It starts off with some poor initial guess that just basically goes down to some fixed point here. And then as we iterate the algorithm, it eventually figures out that actually the best fit is going to be this fit here where you're actually fitting to the correct Lorenz attractor. And this is despite this really noisy, all the noise we put on top of it. And you can see it's sort of a little hard to tell it's still the Lorenz attractor. So that's sort of gives us a sense that the algorithm is working well, and it actually outputs the M that shows you have a stable model. So you can post hoc check that these models are stable as well. So that's the technical details of the algorithm are fairly complicated, but now we can just show some of these provably long-term stable SINDy models. And what this looks like is, so we have some data, Lorenz attractors, might be noisy data. We fit a SINDy model to it, and then we can look at what does the SINDy model look like when you evolve it in time with some random initial condition. And in this case, the model starts with this initial condition way out here. And because we've built in this trapping region, it monotonically falls into this yellow ball, which is our estimate of the size of this trapping region. It falls onto this attractor. And just for fun, I've also shown in blue this ellipsoid where the energy growth is positive. And so basically the system doesn't converge down to a fixed point. It still experiences some positive energy growth while it's inside this trapping region. But this is really nice because now our SINDy model, no matter where our initial condition starts, is guaranteed to fall into the correct region and land on the correct Lorenz attractor we know and love. So that's really great. We do something similar with what's called the atmospheric oscillator. So again, what I'm showing here is the oscillator, and I wanted to point out that the trapping region that we've estimated is like way too big, and so we're zooming in here. And the reason so we still are able to find a model that fits the data really well, gives us a trapping region, but our estimate of the size of the trapping region is too large. Fundamentally, the reason for this is that there's a big scale separation in this system. And so we're estimating the trapping region as sort of in a worst case scenario. And in the worst case scenario, it's sort of basically you take the smallest scale and that's in the denominator. So you end up with these trapping regions which you're sort of overestimating how big it needs to be. But again, if you start with any initial condition out here in wherever you want, it's going to fall uniformly into this region and nicely fit the data. So we still have these nice guarantees. And then for the von Karman vortex street, we can do the same thing. So what I'm showing here is the DNS is in blue, so the direct numerical simulation, the true data. Then we have these analytic POD models from NOAC's 2003 paper. This has been like the standard POD Galerkin model for these for this system for a long time now. And then we have a 5-dimensional and a 9-dimensional SINDy model, and you can see both capture the transient quite well. The 9-dimensional model captures it really well, and of course there's a little overshoot at the beginning, just like there is with the POD models. So this is really nice. We're able to capture this is the total energy of the system. We're able to capture the transient and the long time evolution quite well. And then what it actually looks like in again a three-dimensional subspace of these modes. So we're looking at what's called the shift mode in one direction, and then the first two POD modes, A1 and A2, up here. And what I'm comparing is in the blue is again the direct numerical simulation, the ground truth. The white is our SINDy model. And the yellow here is this POD Galerkin model, which has been the standard in the field for a long time. And you can see from these plots that basically our model is outperforming in terms of correctly getting the long-term dynamics of the system. So these models are starting with a different initial condition than the blue data here, and yet they're sort of converging down to the correct attracting set that we expect. So we're really excited about this. We can also then go back and actually look directly at the vortex shedding. So the top one here is the vortex shedding ground truth. This is the 9-mode Galerkin model, and this is our trapping SINDy model. And you can see it's already capturing the transient timing quite well. It's going to have a little trouble. So this is during the overshoot of the transient. So it's sort of screwing up downstream a bit, but it's going to recover, and then you can see now it's nicely vortex shedding, just as it should. And now we're waiting for the 9-mode Galerkin to start the transient. It's starting to do a little. Great, so the 9-mode model has started vortex shedding, but you're going to see, so not only has it got the transient wrong, but it's also the downstream vortices aren't quite right. There's some sort of shimmering. It's not quite nicely getting this like our trapping SINDy model. So I'll just wait a second here and then I'll change, but this is going to keep going for a while. Great, so this was great news. With our data-driven models, we were able to show provably stable models that can outperform what used to be the state-of-the-art for POD Galerkin models. So I just want to conclude with some last thoughts here. So we've shown that long-term boundedness can be enforced and promoted during regression for system identification methods. This is really, really exciting. This has been a huge thorn in the side of these methods for a long time, and being able to promote these sorts of models is really exciting. We've illustrated impressive performance on a bunch of different incompressible flows. If you want to see more, we have quite a few more examples in the paper I mentioned on the first slide. And we've shown this for systems with these transients and for truly Hamiltonian systems. There's a lot of work to be done here. This is an exciting new field. So we think something similar will work with n-body Stewart-Landau equations. and also a bunch of different algorithms like that map dynamics to a quadratic system of equations, like this lift and learn. And then we want to extend the Schlegel-Nowak result in our algorithm to be able to use alternative low-dimensional bases, such as bases obtained through manifold learning, autoencoders, and Koopman operators. So right now, the way this works is we use, our model is in the Galerkin basis. We're using the proper orthogonal decomposition to like change our fluid velocity u to a set of low-dimensional modes A. And we want to extend the Schlegel-Nowak theorem so that we can use any low-dimensional representation that we want. And many of the modern ones use these autoencoders or other neural network-based thing. So there's work to be done there, and that would be really, really exciting. And then last thing is there are some connections. So nowadays there are some data-driven algorithms that while you search for a model in the data, you also search for a Lyapunov function that proves that your resulting model will be stable. And so there's connection to these sorts of methods, and this is exciting for dynamics that are not just quadratic, because the quadratic case that I've shown you today relies on this analytic result. And so if the nonlinearities are more complicated, we typically don't have analytic results. And then we also we need these data-driven algorithms to discover Lyapunov functions to play the same game. So this is really exciting, and thanks for listening today.